All right, guys, good afternoon. Lesson 8.5, using the Pythagorean theorem. So this is kind of an extension to what we learned in 8.3. It's not going to be that much of a stretch. There is one new big thing, which is the distance formula, which we'll get into here in a second. But first, key ideas. So first is this idea called the converse of the Pythagorean theorem that we see right here. Let me get my pen set up. So converse of the Pythagorean theorem right there. So what it says is if the equation a squared plus b squared equals c squared is true for the side lengths of a triangle, then the triangle is a right triangle. I know, it's really deep stuff. Okay, so let's figure out what this means. So this example they show us right here, let's pretend like this little elbow, the little box in the corner, was not there for a second. Let's say we were just looking at this triangle. Now it looks like a right triangle, right? Like that looks like a right angle. As you guys are probably aware by now, just because something looks like it's true in math, it doesn't necessarily mean it's true in math. We have to prove it. So in lesson 8.3, we learned how to use the Pythagorean theorem to find missing measurements of a right triangle. But in this lesson, what we're going to do is we're going to use the Pythagorean theorem to prove that a triangle is a right triangle. Okay, so the Pythagorean theorem proves that the triangle is right. Okay. So let's try an example down here. All right, so here we have a triangle. It looks like a right triangle, but it's not necessarily a right triangle. So we're going to first identify what we think is the right angle. So we think that, I mean, it would make sense that this would probably be the right angle. So that means that my legs would be right here, 9 and 40. But we can't say it's right just because it looks like it. We have to use the Pythagorean theorem to prove that it's right by saying that the Pythagorean theorem is true for these set of measurements. So since 9 and 40 are my legs, I'm going to do 9 squared plus 40 squared. And then C would be my hypotenuse, which should be 41 squared. So as you can see here, guys, we don't have a missing number here now. Instead, we have all three numbers, and we're just going to see if both sides of the equation are equal. So pull up our calculator here. So 9 squared, that's 81. 40 squared, that's 1600. And then 41 squared, let's check that out. I'm not sure. 1681. So if both sides of the equation are true, which in this case they are, 1600 plus 81 is 1681. So both sides are equal. So therefore, this is a right triangle. Okay, so this triangle right here would be a right triangle proven through or by, let's say by, proven by the converse of the Pythagorean, and we'll just abbreviate that, theorem. And that's our new vocabulary. Okay. So converse of the Pythagorean theorem. So it's right because proven by that. Okay, so let's try this next one. So it looks like this is a right triangle, maybe, maybe not. It's a little iffy, but if it was a right triangle, then this would hypothetically be our right angle. So therefore 18 and 12 are legs. If you're not sure what to make your legs, just remember that the hypotenuse is always the longest side. So C always needs to be the biggest number, all right, which would make this, A and B. Okay, so A squared plus B squared equals C squared. We're going to do 12 squared plus 18 squared equals 24 squared. So go ahead and do the math. 12 squared is 144. 18 squared is like 256 or something. Oh, nope, 324. Okay, so 324 and 24 squared. Where'd my calculator go? Let me just double check that again. Yep. Okay, so 24 squared, 576. Okay, so 144 plus 324 equals 468. So this side of the equation equals 468, but this side equals 576. So these two sides are not equal. Therefore, this is not a right triangle. So that's how you use the converse to prove if something is right. Or how you use the Pythagorean theorem to prove that something is right. Okay? We can say this is not a right triangle because it doesn't prove, it's not proven by the converse, something like that. Okay? So remember, the longest side is always C whenever you're setting this up. Okay, so moving on, distance formula. So the distance formula D between any 2 points, x1, y1, and x2, y2, is given by the formula this. So this is what the distance formula is, and this is actually derived. So D equals distance. This is derived from the Pythagorean theorem. This is what it looks like. It's a little crazy looking. So we have a square root symbol, then we have the second x value minus the first x value squared plus the second y value minus the first y value squared. That's the distance formula. Now, you might be asking, what the heck is this used for? And this is used for, like, let's say, so remember that whenever we're looking at a graph, we can never count diagonally on a graph. But let's say we had a graph here, okay? And there were 2 points diagonal of each other, like so, okay? So we wanted to find the distance of this line. We could use this formula to help us do so, because we can't just count units diagonally, but we can take the x and y coordinates of these 2 points and plug them into the formula, and this formula will tell us how far that line is. Okay, so we're going to practice that right here using our distance formula. So we're going to write it down. So D equals the square roots of x2 minus x1 squared plus y2 minus y1 squared. All right, so looking at our 2 points that they give us here, remember that it's always in order from left to right. So this is going to be x1, y1, and this is going to be x2, y2. So we're going to just go ahead and plug in our numbers. So x2, in this case, I'm going to run a space vertically here. So x2 is going to be -4. The minus comes from the formula, and then x1 is 1, and then we're squaring that. And then we have y2, which is -2. The minus comes from the formula, and then y1, which is 5. And then we square that. So as we work through this, we're going to do everything in the parentheses first. So this is going to be -5 squared, okay, plus, and don't forget about your square root, plus -7 squared. So when we square these negative numbers, they're going to become positive now, which I'll write right here. So -5 squared is -5 times -5 is positive 25. And -7 times -7 is positive 49. So now I don't have any negatives left over. We go ahead and add those two. So 49 plus 25 equals 74. So 74 is not a perfect square. So we are going to leave our answer literally as the square root of 74. Now, sometimes they'll ask you to go ahead and estimate this to like the nearest tenth. So you could go over here to your calculator, type it in, square root, and it's going to tell you about how far away that is. And notice this is an irrational number. It's a decimal that never ends and never repeats. So if they want me to round it to the nearest tenth, I could say, okay, well, that's approximately 8.6 whatever, feet, inches. Either one of these answers is okay, unless they ask you specifically to answer in a certain way. So that's the distance formula right there. Now, if this was a perfect square, like let's say the square root of 81, then I would just say my distance is 9. And that's how far apart those 2 points are diagonally, or how long that line is. All right. So this problem, this is a big ideas problem, and I've taught this for like 2 years now, and I remember this problem every year because kids just complain constantly. It's crazy. So this is a really big problem. So first of all, let's look at this. We'll read the problem here in a second, but let's look at this. So what I see right here, looking at this, I have a triangle. I have 3 different diagonal lines here. I've got 3 different distances, D1, D3, and D2. And they also want me to prove that this thing, well, actually, let's just read it. So it says, you design a football play in which a player runs down the field, makes a 90-degree turn, and runs to the corner of the end zone. Your friend runs the play as shown. Did your friend make a 90-degree turn? Each unit of the grid represents 10 feet. Okay, so this question right here, did your friend make a 90-degree turn? Basically, they're asking, is this a right triangle? That's basically what they're asking you. Okay, so to visualize this, we're starting at this point. This is where your friend starts his run. He runs down the field. Okay, then he makes a 90-degree turn, hypothetically, and you throw the ball. So this is the ball. Okay, so here's my little ball symbol. Okay, you throw the football so that he can catch it at the corner of the end zone. So this is where he catches the ball. So basically, D3 right here represents how far you threw the ball. D1 represents how far your friend ran before he made the turn. And D2 is how far he ran to get to the ball, which is in the air. So they're saying, is this a 90-degree angle right here? So before we can answer that, we first have to figure out how far did your friend run before he made the turn? Then how far did he run after the turn? And then how far did you throw the football? So we're going to have to use the distance formula 3 different times to answer this. So we'll start with D1. We're going to figure out, using these 2 coordinates right here at the start, that's not going to help. Using these 2 coordinates right here and right here, we're going to figure out how far did he run before he turned. We got to know that first. Okay, so D1 equals the square roots of x2 minus x1 squared plus y2 minus y1 squared. Okay, so looking at this, this is gonna, we're gonna say this is, it actually doesn't really matter. We can say that since we started here, we'll call this x1, y1 and x2, y2, okay? And it actually doesn't really matter what you put where, as long as you match up your x's and your y's. So x2 is 30 minus x1 is 60 squared plus x2 or y2 is 20 minus 50 squared. Remember, this is all still square rooted. Okay, so 30 minus 60, that's negative 30 squared plus negative 30 squared. So this is still square rooted. Okay, so we've got negative 30 squared, that's going to be positive 900 plus positive 900, the square root of that. And so that comes out to be the square root of 1800, which I believe that is an improper or an imperfect square, but let's just double check. It is. So we're going to just leave it like this for now. So your friend ran the square root of 1800 feet. Okay, feet. So that's D1. We've done one of 4 steps in this process. So we're going to do D2 now. I'll do this one in green. So D2, we're going to use this point where he turned and this point where he caught the ball. That's going to represent how far he ran from those 2 points. So D2 equals the square roots of x2 minus x1 squared plus y2 minus y1 squared. And this time we'll say that this point right here is x1, y1, and then this point is x2, y2. Okay, so x2 in this case is going to be 80 minus x1 is 30 squared plus y2 is negative 30 and then 20, or sorry, that's not a comma, that's a minus, okay, squared. This is all still being square rooted. So 80 minus 30 is 50 squared plus negative 30 minus 20 is negative 50 squared. Okay, so 50 squared, that's going to be 2,500. And then negative 50 squared is also positive 2,500. So we add those together, 5,000, and the square root of 5,000 represents D2. So your friend ran the square root of 5,000. Okay, one more time, D3. We'll do black for this one. So D3 represents how far you threw the football from this point to this point. So we'll call it like we had it, x1, y1 up here, x2, y2 down here. So the square roots of x2 minus x1 squared plus y2 minus y1 squared. Okay, so x2 is going to be 80 minus x1 is 60. And y2 is going to be negative 30 minus 50. So 80 minus 60 is 20 squared plus negative 80 squared. All right, so 20 squared is 400 negative 80 squared, that's going to be positive 6,400. And all this is still being square rooted. So that's 6,800 total. And that represents D3. Okay, remember these are distance measurements in feet. So now that we have D1, D2, and D3, now we can actually answer the question, did he make a 90-degree turn? Okay, so the way we're going to figure that out is using the first skill we talked about, the converse of the Pythagorean theorem. So I'm going to use these distances I have now, a squared plus b squared equals c squared. My a and my b are going to be my legs right here, d1 and d2. I'm going to put the square root symbols in there. So the square roots of 1,800 squared, because that's the a, it's being squared, plus the square roots of 5,000 squared, and c is going to be equal to my d3 measurement, 6,800 squared. Now, before you freak out about this, keep in mind that when we square a square root, that cancels out and we're left with just the number. Because squaring and square rooting, those are inverse operations. So all of these fancy symbols here are getting actually canceled out, and I'm left with just the basic numbers because I'm squaring a square root. So 1,800 plus 5,000 should equal 6,800, which it does. 1,800 plus 5,000 equals 6,800, which is equal to 6,800. So it checks out, and that means your friend did run a 90-degree turn. So you might be asking that, or you might be thinking that is the most ridiculous thing I've ever seen. And the good news is you're probably not going to see this kind of problem anywhere, but it is a good example of what this is all used for in terms of finding distances diagonally between 2 points on a graph. All right, that's it, guys. Good luck.